All right, we are live. Cool. So welcome back. Last time we got through everything up to digital logic. So being able to design logic circuits, what the individual gates look like, and down to how they're implemented via electronics. So today we're going to kind of bridge the gap of how that actually becomes useful past very simple applications. So to get right into it, basically problems aren't really tenable to us as engineers until we can phrase them as something that's directly relevant. So for a lot of cases, that's just phrasing a problem as a set of numbers. So today we're firstly going to start out with how we use digital logic to build a system that lets us represent numbers using purely logic circuits. Let's see. So I guess the first thing that we have to talk about is kind of what a number system actually is. And I would expect that everyone here is very common working with the decimal system, so base 10. So we're going to take a look at that first. So a decimal number at its core is a series of digits that has base 10. So every digit's place has up to value 10, effectively. Or rather, we can represent 10 discrete symbols by each digit. So that's 0 through 9. And how that breaks down is each digit's place corresponds to some value that's a scalar multiplier of a value of 10. So the zeros place, it's the zeros place because this represents just the set of symbols representable in decimal notation. So we have the value itself is like 0 through 9 multiplied by 10 to the 0 power, which is just 1. So that means for any digits place, we can represent, again, 0 through 9. But as soon as you start chaining these sequences of digits together, things become more interesting because now you can represent values higher than just the base set of digits. So for instance, for the ones place, we're now representing a multiplier of 10 to the 1, or 10 to the first power. So we are shifting that radix, the decimal point. So at its core, we can form some combination of values by using a scalar and moving it over with respect to the radix. And we added all of those together to find the actual value that we're trying to represent. So again, generally, you have a set of digits from 0 to n, and they're operating within some kind of base system. So for decimal, that's base 10. And the value that it's representing is the sum of all of those digits multiplied by their position with respect to that base. And the digit at the kth position holds the scalar multiple times the base to the index power. So the implication here is that this base doesn't have to be 10. We're comfortable working with it, but we can really set this to whatever we want. We also need to recall that everything up to this point using digital logic is capable of representing 2 values. So in theory, we can set this base to 2. And in fact, that's exactly what we're going to do. So when we set the base to 2, we start calling this binary numbers. So base of 2 is synonymous with that. And each of the digits in binary, we also can refer to as a bit. So a binary digit, that's just truncated to bit. And the resolution of the number, whereas with decimal, it's kind of determined by the uppermost position in the set of digits, but also the sum of everything below. But in binary, you can also represent the resolution of a number by the number of bits that describes that value. So if you have a collection of 8 bits, you can only describe up to 255 unsigned values, or rather, there are 255 unique configurations that set of bits can be in. So typically, that corresponds to 255 different values that we can distribute in different ways. So there are a lot of ways that we can configure this set of bits, which I'm going to refer to as a bit field. And the rest of this section we'll talk about different ways that we can organize those bits to mean different things. So the simplest thing that we can represent is called an unsigned integer, and it's just a set of positive integers that also includes 0. So again, that's no fractional values, no imaginary numbers, and nothing below 0. And like we described above, that's simply the relation we discussed. So a set of digits, base 2, where everything adds up according to digit index and the scalar value that is the digit itself. And this, again, starts at 0 and just counts up sequentially. So for our decimal values 0 through 7, we can represent everything via 3 bits. So we have the zeros place in binary counting up. So notice when we're doing this counting that the first bit is always toggling. That's because we're adding 1 every time. So again, 2 to the 0 power. It's either a 0 or a 1. That's the self-description of binary. So again, we add 1 every time. The ones place will count up every time that we have a 1 in the ones place, and we're adding 1 to it. So we're representing value 1 here. We add another binary 1. And so there's a carry value that we add to the ones place now. So this pattern can continue ad infinitum upwards. And that's how we would count up with unsigned integer values. So another observation is that if there are n bits in this value, so there are 3 bits in this example representation, we can represent 2 to the n unique values. So like I mentioned, for an 8-bit value, that's 256 unique values up to value 255 in unsigned integer format. And for 3 bits, that's 8 unique values, 0 through 7. And so the minimum value is 0, always, for unsigned integers. And the maximum value is 1 less than the number of unique values, because we're counting 0. Still with everybody? Just post in the chat if you have questions. So that's the very simple way of representing values greater than 0 that are non-fractional. And pretty frequently, we end up using unsigned integers for representing general sets of bits, just because there's very little in the way of confusion when working with this format. So in embedded systems, we can do things like representing a state as a counter. So we know that a state can never, it doesn't mean anything reasonable to have a state that's a negative number. So we can represent a state with a counting value that's just represented in as a binary unsigned integer. Other things we can do with it, if you're trying to use, we talked about latches. So you can represent a series of latches using unsigned integer values. So if you have like a collection of I'm sorry, we didn't actually talk about latches yet. I'll get there. But if you wanted to represent a bunch of individual bits, you can do so as a collection via an unsigned integer as well, with very little native to the format that would be confusing in doing so. So that's one kind of value we can represent using binary numbers. The second kind is signed integers. So what happens when we extend our representation to values below 0? So if we imagine that the binary number is like a distribution of values spread over the natural number line, unsigned integers have all of the value represented from 0 to some maximum value, depending on the resolution. Signed integers are a little weird because we've chosen to take that that bracket of representable values and shift it lower on the number line. So signed integers are typically biased around 0, and what I'm going to call the left half or the lower half of that set of representable values is in the negative numbers range, and the upper half is in the positive numbers range. So in total, we haven't lost any resolution. However, if we're looking at just representing positive values, we have, because the other half of the integer value range that's representable using that same number of bits is used to represent negative numbers. So signed integers are a little more complex, so I'll go through it a little slower. Like I mentioned, we can represent all integers, positive and negative. So the first way we could think about doing this is using something called sign magnitude format. And that's just using the first bit in the sequence to represent whether or not it's a positive number or not. So the most significant bit is the leftmost bit that I'm representing here. And the most significant bit typically takes, in unsigned integers, the place of the highest value digit. So that would be this one here, down the column. And that's just, again, the bit that weighs the most when you're doing this summation. So here it's the 2's place, and it alone can add up to 4 to the value. So that would be the most significant bit. So again, with signed integers, we could think about using that as the sign holder. So if this were a signed integer, this one value here could represent that it's a negative number. And then likewise, the remaining set of bits could be used to represent the value as if it were an unsigned integer. So for instance, in this sign magnitude format, sign being the first bit and magnitude being the remainder of the bits, you would have a 1 here representing that this is a negative number, and you would look at this like an unsigned integer. So you're representing a value of 1 with a sign of -1. So in total, this is -1. Likewise, with a signed magnitude format, if this is 0, we just look at the remainder, the magnitude, as an unsigned integer, and that also holds value of 1. But with signed magnitude format, you can't just do addition like we did with unsigned integers. And that's just kind of a quirk of the fact that you're trying to separate the meaning of these two fields. So when we actually do the addition here, we look at the sign, and that's -1, and we look at the value, and that's decimal 2. So this actually ends up with -2 when you do the addition, and we were expecting these values to cancel out. So what went wrong? What went wrong is when you're doing the addition, you're kind of assuming that the entire binary number that's represented is part of the computation, so that we're assuming that we can add carry to this decimal column. And that's not the case, because we're using this decimal column as a special value. So we could do something where we tried splitting up the magnitude and the sign into different columns and doing some complex math around that, and it might be possible. but there's an easier way to represent things. And that's the way that's commonly used in most industrial systems today. That's a system called two's complement. So I note that we have an incorrect resulting sign here and an incorrect carry. So we try to remedy this using two's complement. And the way of representing a two's complement number is you start with the unsigned representation of the value, the raw value that you're trying to represent. You flip all of the bits, and then you add 1. So if you start with a decimal 1, you first take the complement. So you invert all of the bits. So that's pretty straightforward. And then you add 1. So in binary. And you do the addition assuming that it's an unsigned integer. So now we've successfully generated the two's complement representation of -1, which is just a bit field containing all ones. And when we do the addition, your first digits place is added, which produces 0 and a carry. So we add the carry. 0 and a carry, we add the carry. 0 and a carry, we add the carry. And finally 0 and a carry. So there's a carry bit that's discarded here. But the result value is 0. So we've successfully found a representation for signed integers that correctly does addition natively. And that's really powerful because we can now represent it with machine hardware very simply. But again, so what I was talking about earlier with the, what if there's an actual carry? So with this addition example, we've kind of represented our bit value as a bit field that's 4 bits. So anything beyond that 4 bits is kind of just ignored because that's outside the resolution of the set of values. If there is an actual carry, what we'd have to do is sign extend all of the values that we're adding up to the resolution that we expect to see at the end. So for instance, if I wanted to use 5 bits of representation instead, the sign extension of this decimal 1 would produce another 0 out here. And the sign extension for this -1 would produce another 1 out here. And the way we can confirm that is by, again, going through the two's complement method of producing negative numbers. And we just assume that the resolution is 1 more. So if we started with a decimal 1, sign extend out a bit to increase the resolution. So 5 bits total. If we took the complement of that, we'd still see a 1 out here in the most significant bit. And when you do the addition down here, as you would expect, that carry just carries into the new most significant bit. For this example, that's another 0 and another 1. So ultimately, it doesn't affect the result. So the number of bits that you're using to represent the number really matters because that determines what the format is going to be. All right, so for a 3-bit unsigned integer, you get that distribution of values with 0 as kind of the median value, like I was hinting at earlier. So 0 is represented identically because you can't really take the complement. 0 is like a special case. If you're trying to represent 0, then if you took the complement and then add 1, you're going to result in 1, which doesn't really make much sense. So basically what I'm getting at is you can't have a negative of 0. So 0 is the special case where you don't want to apply this two's complement approach to generating a negative number because it's not really representable here. But for all of the other numbers, you can find their mirroring about 0. So 1 you can invert, as we saw. 2 you can also invert. So all of the positive numbers do still count up as if it was an unassigned integer. And the negative numbers also have their own pattern, but rather we're counting down to the largest value representable, outside of that most significant bit. I'm not following the logic here. So, sorry, for anyone that's not in the chat. So if we wanted to do yeah, so that the value represented, so the first value of all binary ones plus that, right? So this is decimal 1. The way we can confirm that is we start with the unsigned integer, we flip all the bits, we add 1, right? So if we've inverted 1, so if we want the negative of 1, we now have its representation. So yeah, so if this, and this is, there you go. Right, so if we're adding -1 and 1 true values, we should expect a 0 value in chat, right? Yeah, so yes, so the 0 doesn't have a meaningful representation of -0 in this format, and that's, yeah. If you try to invert 0, you're just going to end up with 1, which doesn't really make sense. But we could do this with other examples too, right? So we can represent decimal 2, and following the quick table, decimal -2 should invert as well. So you add the zeros, gives 0. You add the 1s, so that gives 0 with a carry. Suppose I could represent the carries up here. Now you add the 1s and you get 0. Invert 0. Yep, you're correct. Right, okay, so we have an unsigned integer representation and now a signed integer representation that works with yes. Yeah, so we have an unsigned integer representation that gives us positive values for simple cases, a signed integer representation, which gives us positive and negative numbers, but they're still non-fractional. The last thing to represent would be fractional numbers in this mix. Oh, I missed this section. So yeah, we can still express to the n values with n bits. And like I mentioned, the range spans with 0 as the median. So we extend upwards. So we kind of count 0 as an unsigned value, in this case, so a positive value. And so the negative range has 1 digit's value higher than the positive range. That's one quirk. But you can still represent the same number of unique symbols. So with 3 bits, you still get 8 possible states that you can represent. All right, so the last thing to think about, that's practiced in implementation is something called floating point numbers. And this is a way that we can use to represent fractional values that either are positive or negative. There are other ways to represent fractional values, and this is just one of them. It also happens to be the most common, so I'll lead with it. So floating point represents things kind of in this system where we have some what's called the significand and you're multiplying it by some base value to an exponent. So the significand contains the significant figures of the value that you're trying to represent. So let's say we have decimal 2.5. The significand would contain that set of digits 2 and 5, at least in the decimal system. And the base and exponent combination move where you put the decimal point, or more generally, the radix. So the place where you represent values that are no longer whole numbers. So for 2.5, that decimal point is the radix. You have 2 as your positive integer value and 0.5 or 1/2 as the fractional values beginning, or rather as the first fractional value that you're adding up. So 1.2345 has the significand containing, again, all of the digits themselves. We're in base 10, so we place that binary, or that radix point here. So 2, 3, 4, 5 are representing fractional values. And that radix point is the inflection where you get, again, all positive or negative integers above it and all fractional values below it. So in this system, we could represent the number in base 10 with an exponent of -4. So we take the significand, assuming it's all like whole number integers. And so we start with the radix point. Oh yeah. Oh yeah. We start with the radix point, after the least significant bit, or the least significant digit. And then we apply the base and exponent combination. So 10 to the -4th moves the decimal value 4 places. And then we result in our fractional value. So when we talk about floating point, it's floating because the base and exponent combination can move that decimal point to basically anywhere in the significand. With other representations like fixed point, you can't really do that. I won't go into it in detail, but because the floating point number, or the floating point representation, can have that radix move around the significand, you have kind of a flexible resolution, or a distribution of resolution of the values that you can represent at any point. So when we were talking about unsigned integers and signed integers, the resolution of the number is evenly distributed across the set of values. So we have between each value, there is an increment or decrement of 1 always. So, between binary states, you're not going to be adding some different value. It's always a shift of 1. But with floating point, that's different, because we still have a set of, like a fixed set of bits, or a fixed width bit field that can represent values. But now we need to spend, for instance, if we wanted to increase the exponent a lot. So this is a very large value. We have less bits that we can use to represent the significand. So that's just like the raw number of positions. So the raw number of bits that we have to use to represent something. So in effect, that means that all of our number representations in floating point have some tolerance that we can use. So they're all estimates of the actual fractional value. So the most egregious example I can think of for this is if you have like an irrational value that you're trying to represent. So like 1/3 in floating point is always going to be an estimate, because you have, like, if you're trying to represent that as a decimal number, you have an infinite significand. in theory, right? So you have one trailed by a bunch of threes, but that trailing three never ends. So what we have to do is cut that off at some point. And when we do the calculation for the floating point number, typically we just we'd look at the exponent first. We'd say, you know, it's we have some fixed significand that we're trying to fill, and we know that the radix is kind of at the leftmost position. So we have some large exponent and some significand that can fill the remaining number of bits. So it might be, you know, 1.3 to the 10 to represent some number. Or to represent that 1/3 value. But the general idea is there's a cutoff, a tolerance, or an estimate that we have to do to be able to represent, to be able to pack some fractional value into a set of bits. Let's see. Fixed point doesn't really have that problem. So it has an even distribution of values, just like we saw with both unsigned and signed integers. But the trade-off for fixed point numbers is that because you have a fixed size exponent and a fixed size significand, there's a much smaller range of numbers that you can represent. So again, we can't have exponents exceeding some size and significand's exceeding some size. Let's see. So there's a format for floating point numbers specified in this standard. So when I release the notes, you can check this out in detail. But IEEE 754 is kind of the system that industry uses generally to represent floating point numbers now. So this gives us a common binary representation that I can talk about. So I can talk about the innards of the number format now. But there are generally a lot of different ways that you can represent floating point numbers. There are some, like I mentioned, other systems for representing signed integers, but in practice, only 2's complement is useful, again, because of how the addition works out. With floating point numbers, there isn't really a smooth, like parsimonious way of doing addition. Like everything is going to be a little complicated of an operation where we're going to have to break apart the number. So it ends up kind of a matter of just convention, how we choose to represent that floating point number. So the reason that IEEE 754 floats exist is because the distribution of values that you get as representable works with kind of the use cases that we'd commonly be seeing with applications that want to use floating point numbers. And that's like, if we wanted to represent financial values, we might have to use a different system because, you know, if you get small enough with your increments of values, then again, we run out of bits to represent either the exponent or the significand. But that's kind of a topic for later. So first I should just describe what IEEE 754 is. So we have this concept of a floating point number that's this kind of relationship. IEEE 754 gets rid of that concept in a way. We are instead representing things in a sign magnitude format. So the first bit represents sign and the remainder is magnitude, but the way we represent the magnitude is as two different values. So we have an exponent that's a fixed number of bits and a fraction that's also a fixed number of bits. The fraction is in a way representing the significand, and the exponent is in a way representing this exponent. However, there's a little bit more complicated relationship than that, because IEEE 754 adds in this bias value. So the true relationship when representing some fractional value via IEEE 754 is this relationship. So if we had described this bit field, S would be the most significant bit. I think it's exponent following that. It could be fraction though. So we have a sign bit followed by a set of fraction bits followed by the exponent bit, for instance. And that's what I'm representing using these symbols S, E, and F. So the value we get is, if we're treating S as a signed binary value, so it's either a 1 or a 0, this relationship basically gets us either a 1 or a -1 multiplier for the rest of this value. F being the fractional value is, if we look at it like a significand, then it's going to be an unsigned integer value. For the sake of this relationship, we're treating it as a decimal number. So you look at F as unsigned integer, you find its decimal value for the sake of this equation, and then you add 1. And lastly, you have the effect of the exponent. Like I mentioned, there's a bias value so that we can get this exponent kind of centered around we're trying to move around the range of representable values using the exponent. So if the exponent is an unsigned integer, we need its sum using this bias to also be able to represent negative numbers. So up here we had in base 10 an exponent of -4, but we can't do that using an unsigned integer. So what we do is instead subtract a bias from it. And because we're working in base 2 for binary, then 2 becomes the base in this phrase in the equation. So let's see, I think we are talking about 32-bit floating point values, in which case the bias is just 127 by convention. So this is according to the standard. Yeah, so here I've been describing a 32-bit floating point value in IEEE 754. So that's, again, 32 bits to represent the whole number. There are other representations that use different resolutions. So you're going to have like a 16-bit float or a 64-bit float. But typically we refer to those as different kinds of values. So if a floating point number is 32 bits, then we can call a 64-bit representation like a double precision value, because you're getting, in theory, twice as many states that you can represent. But yeah, for this example, and really just for the bias and the number of bits that are allocated to each of these fields, we're assuming 32 bits, which is fairly standard across a few different machines. So in this representation, it has some quirks. Whereas with unsigned integers, 0 only has one representation by convention. IEEE 754 floats actually have 2 different representations of 0. So you can do it with, let's see, yeah. So it's because we're using sign magnitude format. So the exponent and fraction, if it's all 0, this equation kind of falls out, and your sign doesn't really matter in that case. So you can have technically a -0 and a +0, which doesn't make sense for a lot of engineering applications. And it's more of like an artifact of the format. You can represent infinite values by convention if you have an all 1 exponent or and a 0 fractional field. And again, you can use the sign bit to represent whether or not that's positive or negative infinity. If you actually put it through this equation, it doesn't result in an infinite value, but we're calling it by convention that this state represents infinity for practical purposes. So if you wanted to do, if you have a condition where somehow you're dividing by 0, in some cases it's useful to indicate that that's a value that's going to approach infinity. So the return value, if you're doing that kind of operation with a float, could be some infinite value if you wanted it to. So there are certain systems where that can be the case. In almost all systems, again, a divide by 0 just results in an error. Like it's not really representable in our natural language or our natural description of math, but again, there are cases where a representation of infinity is useful for some applications. And the last kind of special case is called number, not a number. You may have seen like NaN or NaN. If you've worked with MATLAB before, if you've worked with floating points in the past, the fraction value, yeah. So the fractional value is an unsigned integer field within the IEEE 754 float. It isn't actually representing a fraction. They just call it fraction. More realistically, it's the significand. So it's what we described earlier. It contains all of the significant bits. So that's all of the bits, all of the digits that come before the radix. So all of the integer values. And we add 1 to the fractional value because that's part of the convention of IEEE 754. I'm pretty sure it has to do with the way that you can represent like numbers that are close to 1 or just below 1. So for instance, if we wanted to do, if we wanted to represent 0.5, you could have a fractional value of 4. So you get 5 as your significant bits, and then you would shift the radix so that you can have 0.5 rather than 5, right? So this 1 exists, like in theory we could do it without the 1 there. To tell you the truth, I don't really know why they did this offset, but it is part of the standard. And really, we're in practice, I have not yet found a reason to dissect a floating point value. The real reason I'm presenting this is because it is a standard that people stick to, and it is useful if you want to create your own floating point system. So like I mentioned, IEEE 754 is just one standard that can be used to represent these numbers. But it fails in some cases. So if you have an uneven distribution of values where some values just straight up aren't representable, in some of the cases, the tolerance between the number you're targeting versus the number that is representable is too big for your system. So applications I can think of are like, if you're doing astronomical calculations, values get either really big or really small in that kind of a system. Or if you're doing like computational chemistry, you're not really going to want to use IEEE 754 because either really big or really small values, and some special cases in between, have really poor tolerance for representing a true value. So you'll probably want to roll your own float number, and you would not want to use IEEE 754. So yeah, this addition of 1 is a little arbitrary. Yeah, yes, programmers really like integers because you don't have to deal with this tolerance problem. You know exactly what the resolution of your number is for a fixed number of bits. Plus, there's the native representation is fast to work with because you can do this arithmetic using just digital logic, as I'll get to. But yeah, floating point is complicated, but useful for a lot of applications where you absolutely need to represent some kind of fractional value at the computer level. That's not all cases. So I would recommend, from an embedded systems engineer point of view, stick to integers for any case that you really can. Yeah, so I note here, it's really uncommon to need to manually convert to and from floating point. So really, this is just for your edification, what's going on under the hood of a fractional value. Let's see. So the last thing that I need to talk about with respect to binary numbers is what we call bitwise operations. So before, with digital logic, we talked about certain kind of logical gates that you could apply to single signals as inputs. So if I go back up to those, we're assuming that A and B are discrete binary values. Another way to look at this is that the inputs A and B are individual bits. So you have bit A and bit B that are being applied to this operator, and that operator produces some result. When we're representing binary numbers, I had also referred to these as a bit field. So these are a collection of bits. You can also apply those same binary operators to binary numbers. So with a bit field, really what you're doing is, with a bitwise operation, is you're applying some digital logic operation to all of those bits in the field simultaneously. So when you're doing a comparison, let's say for unary operator like not, so not of a simple 1-bit value is just the inverse of that bit. Not of a set of bits is just the inverse of each of those bits at their location. And that also applies to the operators that use two inputs. So we just treat for a bitwise and or XOR, we treat the inputs as each bit that's in the bit field, right? So you take for and, you would do the and of the bit that's in a certain digit, and then you the second input to that and would be the digit from the second number in the same index, and that's pretty critical. So here we can break this down as if it were the digital logic representation. So we have bit A is 1, bit B is 1, so the and of both of those values is 1. Now we look at the next column. The and of input 1 and 0 is going to be 0 because they're not the same value. So as you see, we're applying the digital logic operation that operates just on 1 or 2 bits. We're just distributing this over each of the digit positions for your binary number. So that's one way that you can kind of manipulate individual bits within a bit field. And I've been talking about it like a bit field. Technically, you can do this with both unsigned, signed, and floating point numbers. But it doesn't really make sense in the context of floating point numbers because we've dedicated like sections of that bit field to mean certain things already. And with signed operations, you can still apply these bitwise operations. But I find in practice, there isn't really much reason to do so using a signed value. Because again, there are configurations of that signed value that, rather configurations of the bit field representing that signed value that we're taking to mean something. But with an unassigned integer, there isn't really, by convention, anything special about any of the individual bits. So typically when we talk about bitwise operations, the actual value you're using to represent that number is an unsigned integer, at least from a programmer standpoint. From a machine standpoint, a bit field can just be like a collection of stored state. So when you're doing a bitwise operation, all it requires is some collection of bits that work together. I think that was it. There's so these are all representable with digital logic. there is a new kind of operator we can also apply when we're looking at collections of bits. That's called a bit shift. So one way to look at this operation, the reason we can't do this with digital logic is because it doesn't make sense. So if you, a bit shift is moving, it's as if you're taking all of the set of values and changing their index. So for instance, if I say we have place 3, place 2, place 1, and place 0. And we have some binary number, right? So we have 0, 1, 1, 0. So if these represent the index of the number and these represent the values, you could do a shift operation that takes all of these values and moves them, right? So let's say I added some more places to this, right? So right now we don't have any values in the 0 or 5's place, which in practice doesn't make sense, but just as a demonstration, if I wanted to shift this number, I could put all of the values, I could move all of their indices, right? So we now have the same bits represented at a shifted set of indices. I could also do the same in the opposite direction. So with a left shift, we would move all of these values over one index. With a right shift, we would move them over in the opposite direction, one index. This is useful if we wanted to do very quick multiply by 2. So yes, if we shift left once, we are multiplying by 2. If we shift left, or if we shift right once, we are dividing by 2. And that's just kind of an artifact of using binary number representations. I haven't heard of anyone using bit shifts with decimal values before. But so in practice, what a bit shift is doing is moving the significant values around by some index. So actually, this is a good question. Do the rest of the places get autofilled to 0? If you are trying to draw value, if you're doing a left shift, yes, absolutely. So, if we had binary value, sorry, I'll bring up that representation I just had. If we have a binary value that starts here, so we're representing unsigned integer 6, right? If we shift left, we're multiplying by 2, so we should have some representation that contains 12, right? So, so in the 3's place, that's 2 to the 3rd, that's 8, and in the 2's place, that's 2 to the 2nd, so that's 4. Sum those, and we have 12, right? So we should have a 0 pop up here. With right shifts, it's a little weird because that question becomes very relevant. Like, what pops into this most significant bit for a rightward shift? So if we took, let's make the values a little more interesting. Let's say we have, in unsigned integers, this value, let's see, that's 9. No, yeah, that's 9. In signed integers, it's a different beast entirely. So if we wanted to, oh yeah, sorry, I guess I should start it here. If we wanted to do a rightward shift, we could end up with one of two results. We could end up with a 0 here, or we could end up with a 1 there. And which you do is actually up to the operator. So as I talk about later, there's the concept of an arithmetic shift and a logical shift. A logical shift would introduce a 0 in this location. So that's kind of assuming it you don't have a representation that means a number in your bit field. This is useful for cases where your bit field represents something like you're doing something with the individual bits. So let's say you just want to have a 1-bit here or a 1-bit here, and you do a shift operation to move, which to toggle between the state of 0 or 0, 1. So you can very easily toggle which of these bits is active just by doing a shift operation. And that would be a really fast way of doing it. That I would recommend doing a logical shift for, because if you did an arithmetic shift that introduced a 1, when you did the rightward shift of this value, you would get a 1 here, which may be buggy for a certain application. So the kind of shift you're doing actually matters. So wrap, yeah. So with an arithmetic shift, the key is kind of in the name. So you're doing arithmetic. So you're assuming that this bit field that you started with has some meaning. It has an association to a number that you're trying to represent. So when you're doing an arithmetic shift, yes, it sign extends. So if you're doing an arithmetic shift on a value that has a 0 in the most significant bit, that 0 will get sign extended. So an arithmetic shift for a value with a 0 in the most significant bit looks identical to a logical shift. So they would both produce the same. Both kinds of shifts would produce the same value. A sign extension is basically just taking the most significant bit and padding everything to the left of it. So if we, let's say we had 7 positions, so 7 bits of representation. Well, okay, 8. And we had a value down here that was just unsigned integer 1. If we wanted to sign extend this, it would just mean placing zeros at the rest of these positions. But if we have a value that has a 1 in the most significant bit place, if we wanted to sign extend this, you would pad it with 1s because it matches the most significant bit that we started with. So that is sign extension. Does that make sense? Yeah, so whether or not you actually do sign extension is up to you as a designer, either of hardware or with shifting operations in software. But it is a distinction to be made aware of. So that question was really relevant. You guys can actually see this notepad instance I'm pulling up, right? I shared the whole screen and not just, yeah. Okay.
Yeah, you're good.
Cool.
Yeah, we can.
Wrap around. Yeah, rotate is a different kind of operation. It is akin to a shift. I didn't actually talk about it here, but yeah, so a rotate would be something like if you have, say, a 4-bit field and you want to rotate it right, you could do, you would wrap this one value back to the most significant bit and then just shift the rest. Likewise, if you do a leftward rotate, then you could get the same result. So there are cases where it's useful. The reason I don't talk about it is because it's not typically offered in programming environments. You can do rotations. It just requires different combinations of operators when you get to that state. So yeah, some computers do offer rotate operators that do this.
So that's like all the possibilities, basically, right? You can move, you can shift it and then put a 0 there, shift it and put a 1 there, or shift it and put like whatever you route around there.
So yeah, whether or not you're actually placing a 1 in the most significant bit when you do a shift, a rightward shift specifically, is up to the value and which kind of shift you're doing. It isn't arbitrary. You can't just place a 1 there unless you do that as a separate operation. But there are conditions where a 1 will appear there, and that's if you're sign extending. So that's if you're doing an arithmetic shift and you already have a 1 in the topmost place, or in the most significant bit.
Okay, so it's not always a
no, it's not always a 1.
Arithmetic shifts?
Right, so
Okay.
arithmetic shift just preserves the most significant bit, or rather the state of the most significant bit. So
Okay.
It'll preserve a 1 if there is a 1. But if there's a 0, it also preserves the 0.
Cool.
But for clarity, again, leftward shifts always introduce a 0. I know that can be a little weird, but there are cases where this becomes relevant. A lot of cases, you don't really need to use them. But I'll return to this when we start talking about programming in terms of like C programming. Yes, arithmetic shift preserves the sign via sign extension. So I think we're actually a little short on time right now. So now that we have some kind of way of representing real engineering values in the form of numbers, we can start putting together numbers and digital logic to produce something that actually works with these number representations. And the way we do that is by slowly building up elements of a computer until we have a computer. So this session is going to be a little less organized than the others, just because there's a lot of ground to cover. I'm not going to cover everything in excruciating detail, but I want to give you enough information so that you can see that it is theoretically possible to put a system together that does these things. So first, we're going to start with computer elements. And to really understand computer elements, we have to introduce this concept of a finite state machine. So a finite state machine is like a theoretical model of how something operates. And what it's describing is a system that has a fixed or finite number of operating states. So what I mean by that is you need to be able to represent your system states discretely. So for instance, you can have a door, and if that door is your system, then you can represent it's either open or closed. If you care about that, you could also represent it as closed, opening, open, and closing if you wanted to. But these are all discrete states that system is in. And for at least this example, there are a fixed number of states that you're trying to represent. So a finite state machine would not be a good way to represent like a chemical reaction, because the number of states needed to represent that chemical reaction kind of exceeds our modeling capability. Unless you're talking about, not reacted versus fully reacted. That would be fair, but not really useful to us. So a finite state machine is really useful in kind of understanding how a system can flow between different states. So understanding the conditions that are necessary to change states and what effects changing state has on the system. So we typically document them either as state transition tables or state diagrams. And that's just two different means of understanding the model. But again, in both cases, it's really critical to understand the conditions of transitioning between states and the effects that transitioning has. So my example here is for a turnstile. So like one of those paid gates that you go through to enter a train station, a ride, or so on. So we can represent two different states. Here we represent the locked state or the unlocked state. There are, again, more states that we could represent, but maybe we don't care about. So we have the locked state if someone inserts a coin that causes the transition to the unlocked state. Likewise, if someone inserts a coin while the system is already unlocked, that doesn't do anything. So we have this self-referential arrow here that points back to the unlocked state. If the system is unlocked and someone pushes on it, they go through the turnstile and it self-locks again. And likewise, if someone tries to push on the turnstile when it's already locked, nothing happens. So we have that self-referential arrow here. This last little indicator here, it just means that the turnstile starts in the locked state. And we could also represent this as like a bubble that says init or start. And that's just the initialization of this finite state machine. So with the state transition table, we get the same information. If you're in locked state and you insert a coin, you can transition to the unlocked state with some side effects. This state diagram doesn't represent these side effects, but you can. Typically, it's done by like drawing a line underneath the conditions and describing what happens on the transition. So something that's important to note is that states themselves don't represent effects. The transitions represent effects. So once an effect has occurred, you're in a new state. So state machines are really useful when developing new systems. They allow you to kind of explore behavioral requirements of that system. And again, this is assuming the system is capable of change. If it's something like a mathematical operator, that's always true regardless of what inputs you give it. Like a mathematical operator doesn't have any state because it's not changing. But if you have something like you want to represent a light bulb or something that can change what it's representing, that's something that you want to model with a state machine. So you'll see how this applies very soon when I start talking about computer elements. So again, we had our method of representing numbers now on top of digital logic. We have this concept of a state machine, so a way of modeling and representing systems that can change over time. So let's put those three things together: digital logic, binary numbers, and state machines. So the first thing that we can represent is something that holds value. So with digital logic, you have the inputs and outputs to the system, and the system is just a reflection of the inputs. But if we want to do math, then we need a way of representing this collection of bits all at the same time as another collection of bits. So the way to do so is to create storage elements. And the simplest kind of storage element is called a flip-flop or a latch. And it is a computer element that's capable of storing the state of one bit. So that storage means it's changing state such that the output is now independent of the input up to a degree. So basically, there are conditions which can cause the output to change, but it doesn't have to change. And the way I can represent this is called an SR latch. So it's a combination of digital logic gates where you can represent the output value as, again, a function of the inputs, but there is a state in which the output doesn't change. And that's how we end up getting our value storage. So if you follow the logic through with these NOR gates, the animation is pretty helpful in that. Notice there's a state where you apply value to one of these inputs, R or S, so reset or set. And then you remove that input. So you have a high value that changes the state, then you can actually remove that input and the output does not change. This is the essence of why we actually need a state machine to represent this system, because there's now a difference in mapping between an input and an output. So it's no longer a mathematical function where one input maps to one output. You can now have multiple inputs map to potentially multiple outputs, hence the state machine. So for this SR latch, you have inputs S and R, or set and reset. And the kind of the truth table, or the state transition table that we're representing here, shows you how we transition between these states. So if S and R are both 0, then it holds the value that's currently represented at the outputs. Only when you're applying either S or either R do you actually change the state of the output. For this system, applying both S and R values as high is indeterminate. So we just make sure that systems that use SR latches don't apply S and R at the same time. But using these two inputs, we can store binary value of 1 or 0. And I mentioned the main value of this system is that when S and R are both 0, you still have that same value that you've last applied at the output. There are different kind of latches. So an additional kind of latch is called the gated D latch. The inputs are now different, so the state machine has changed slightly. The function of a gated D latch is basically there's an enable signal, and that enable allows the system to match the state of D when enable is set. So we can represent that with the state transition table. If E is 0, then the output value doesn't change for this latch. If E is 1, then the output value will always match input value D. So in effect, it's a way of, it's another storage method for 1 bit, but the inputs to the system are slightly different. Yeah, so the second half of the gated D latch does look like the SR latch, but this SR latch is implemented using NOR gates. This one's using NAND gates. Again, you can follow the logic through to verify the state transition table, but this is the ultimate function that we get out of a gated D latch. So we can increase our complexity a little bit now. The D flip-flop is kind of a derivative of gated D latch, where now we are exposing far more inputs and outputs to the system. So yeah, there's a way of representing this using NOR gates instead. And I'm pretty sure that just inverts which of these will be the output. But in a D flip-flop, you're also exposing set and reset signals. So you can manually change the state of these outputs, or you can use the method of gated D latches to follow the value of D. So in particular, there's also some other logic for a D flip-flop where you can follow the edge condition. Instead of an enable signal, this is now a clock signal. And by that, it means it's referencing the edge condition rather than the state of the clock signal. So to make that a little less confusing, with a clock signal, you're looking at when it changes state. So For binary representations, you can either have a signal being 0 or 1, but there's also the transition condition between those values that in the ideal case produces like what we call a rising edge or a falling edge. So if you go from 0 to 1, that's a rising edge, and if you go from 1 to 0, that's a falling edge. The D flip-flop, at least that I reference, it gates the input D based on the edge condition on the clock line, rather than it being a straight up enable signal. And then also exposes set and reset inputs. So whether or not you actually connect to all these is entirely up to you. So you can use a D flip-flop as if it's an SR latch by just not connecting D and not connecting clock. Likewise, you can completely ignore this set and reset pair of inputs. You can even ignore the output queue or its component not queue. But point being, we have a way of representing persistent storage that combines all the good features from an RS latch or a gated D latch. So this thing can represent a stored bit. So what happens when we put them together? So if this stores one bit, then a sequence of them can consecutively store multiple bits. And if they all reference the same clock, that means we are either setting or resetting them at the same time. So using a D flip-flop, we can produce something that's known as a hardware register. So this hardware register is just a representation of a bit field. So it is a set of D flip-flops is one common implementation that stores bits all at the same time. So if you would imagine this circuit, we have our clock signal on this line, and we're ANDing it with load, which in this case is a signal that represents that we should do an operation where we store bit states. So if we take the AND of these signals, if clock is always oscillating between states 0 and 1, then we'll, at certain times, we will have rising edge conditions. And when clock and load are both, when clock is at a rising edge and load is high, then this AND will produce that rising edge value as the clock inputs to all of these D flip-flops. When that happens, when we have a rising edge, again, following the state transition table, each of these flip-flops will look at the value at D. So in this case, it's these set of 4 in values that are connected to each of these flip-flops at D. And then our output value, or Q in this case, will match those input values. So based on the fact that we're using a D flip-flop, once we've stored that output value, if we remove this load signal, then the set of flip-flops will now all store our collection of bits. So how this becomes really useful is now we have a way of persistently representing collections of bits, and therefore ways of representing these binary numbers. There are also a number of uses for hardware registers that I'm not really going to get into, but we'll talk about some of them later. Yeah, this section at least is where all of the theory we've talked about starts to come together, where we can actually start to build systems using this stuff. A quick note is that when we have like a collection of input lines to a system like this, and all of these input lines are related, generally we talk about this as something called a computer bus. So if I shorten that, it's just a bus, but a bus is a collection of data lines that all collectively mean something when they're together. Good meme. So generically, we can talk about this as if it's a form of memory. So memory in the broadest sense is a collection of bit fields. So this is one way of representing a collection of bits. when you have collections of these collections, then you start having what we talk about with memory. Another way to look at it is just like one really big bit field, but that's besides the point for now. In memory, so if you would imagine consecutive hardware registers, so we have like groups of these flip-flops that can represent numbers, but they can also represent generic bit fields. If you have a collection of bit fields that are all the same width, so they store the same number of bits. So we have like, imagine a table that has uniform length fields. You would have like the first row, the second row, and the third row. Each of them is its own bit field that contains some number n bits. We can call this memory, and because it's storing information, but it's also addressable. So I can refer to the bit field at row 0 or row 1. How we delineate these rows is entirely arbitrary, but the important part is that we can address them. So we can talk about the bit field that's stored, again, at this row or this other row. Generically, memory also has these operations of storing and loading. So to load something means to extract information from it, and to store information means to put information into the memory. So a hardware register isn't a perfect representation of this because you're not separating the bit field that it's representing into like uniform length chunks. Hardware registers store state, and then we can use them to build up memory if we wanted to. But again, memory is something that's addressable and that you can store information into or load information from. There are two other classifications of memory that we can talk about, and that's kind of a parallel classification. There's volatile memory, where the values that you're storing are only kept while the circuit has power. And then there's non-volatile memory, where those stored values persist even after you remove power from the circuit. We'll talk about these in detail later as well. So this is just for representing stored values. That's you wield it up from a latch using digital logic until you have something like a hardware register, and we can use similar techniques to produce different kinds of memory. The next kind of computer element I want to talk about is called a multiplexer. A multiplexer is a way of taking a number of data lines, selecting one of them, and giving that as an output. And its complement, the demultiplexer, also exists, where you take like one output, you select a data line that you want it to be sent to, and it is sent to just that data line. So multiplexers and demultiplexers are stateless. So they're not changing over time or based on inputs. They're rather closer to mathematical functions where they don't change. So S1 and S0 are the selection signals in this case. And based on the combination of selection signals, the internal circuitry of the multiplexer will connect you to one of the outputs. So for instance, if S1 and S0 by convention are 0, then you connect input A with output Z. So that's represented in the truth table by Z matches A, and so on. Pardon me for a minute. So this becomes useful, for instance, if you have a data bus, but you're only interested in one of the bits in the data bus, you can select which bit. Or for a demultiplexer, you have some signal that might always be high, it might be a clock, and you have some binary number representation that selects a signal. So if I extend the number of outputs that this multiplexer has, you could see that S1 and S0 together actually count up in as an unsigned integer. So we could use this if we had a binary number representing a state of a machine that we're trying to develop. we could use that state value as the input to a multiplexer in order to march the system through a signal that represents each of the states. I don't really talk about multiplexers later, but hopefully you can see that there is value in having this kind of a structure. The implementation is pretty straightforward as well. It's just you're using these selection signals to pick only one at a time. So it's a combination of, I'm guessing, AND gates. Like for selecting D, you would have like a series of AND gates where S1 and S0 are true. For selecting C here, you would have something that says well, you would take S1 and not S0. But hopefully that makes sense. You can also start building up arithmetic operations using digital logic gates. So what I've represented here is called a full adder. There is also a half adder, but I won't get into it because full adders are useful. So an adder is a circuit representation that adds 2 bits together. And as we talked about with our binary number representations, adding includes using a carry value. So a full adder takes into account the 2-bit inputs, A and B, but also the carry value as input. And the reason that's important is if you have, no problem. This video will be up later as well as the lecture notes. So you can review if you miss more. So the adder takes into account the previous carry value. And as we talked about with our binary number representations, that's really important because you need to take into account the carry value from previous bit additions. So this truth table falls out from this particular circuit representation. The output of the adder is therefore the sum value. So that's either going to be a 0 or a 1, and the carry value also 0 or 1, based on the conditions of the input. And if you look at the truth table, it's basically just following the addition, the simple binary addition that we did before. So if we have A is 0, B is 1, and we have a carry, you are adding together B and the carry to get 0 at the output. Oh, that should be 0. I'll fix that before releasing this. Point being, there is a digital logic representation that we can now use to add together 2 bits with carry. And the way we can extend this into representing binary number addition is basically just by chaining them together. So you take the carry value of one of these full adders. So it has some carry input that is provided to it by some system on top. It has our 2 inputs. We do the full addition. We get the sum for that bit, but then we send the carry value to the next adder. So if if AN is the first binary number that we're adding and BN is the second binary number that we're adding, we'll get sum N. And that's some binary number that represents the addition of both of those 2 inputs. There are a bunch of other arithmetic operators that we can implement. For time's sake, I chose not to show their implementations, but hopefully by visualizing this circuit is, you know that it's possible to build up the rest of the arithmetic and other operators, again, using digital logic. The last thing that I want to talk about for computer elements is timers, counters, and clocking. So we talked briefly about a clock signal, and that's something that a signal that can switch between 0 or 1 at a very fixed frequency. So what that ends up looking like in practice is a square wave. So you have a transition that goes from, I'm going to call underscore low and I'll call space high. So you have something that is constantly shifting from logic low to logic high, and it has these edges that are either rising or falling. A clock signal does this at a very fixed frequency that is known, and that's useful for a lot of different applications that I'll get into later. But we can use this to build systems like counters and timers. There are a couple ways that we can actually produce this signal, though. Before we even get into transistors and special dedicated elements, we can actually use resistors and capacitors to produce a clock signal. It'll be ugly, and it'll need to be like signal conditioned so that we only get values logic low and logic high. But it is possible to get an oscillation out of a resistor capacitor pair. And we use the resistor capacitor values to set the frequency of this oscillation. And then I mentioned, again, we do some signal conditioning. There's also another kind of circuit element that we can use to generate this clock signal. And that's known as a piezoelectric crystal. So the specifics of how piezoelectric crystals work, I'll leave it to you guys to look it up. But effectively, it's a deformation in the crystal is capable of producing a voltage. And if you're applying a voltage versus receiving a voltage, you can induce the crystal to wiggle. And via mechanical oscillation, that wiggling occurs at a very fixed or very stable rate. Yeah, I linked a video here that you guys can check out later. But point being, it is capable of generating some kind of clock signal. So we can use a clock signal to drive something known as a counter. And a counter is really just a register, like a hardware register that contains some value, and that value increments whenever our input signal toggles. So this isn't immediately clear, but these are D flip-flops. And then we have an AND gate and an XOR. And the outputs from this system, which I've represented up here, you can also feed into a hardware register. But basically, when this clock toggles, we add 1 to the system. And what that means is we have something that counts every time this clock signal toggles, at least for this circuit. So this combination, a clock signal, some combinatorial logic, and a hardware register, we can use to represent counters. And lastly, we can represent something known as a timer. So if we wanted to do something when this counter value reaches a certain level or doesn't reach a certain level, then what we could do is have a separate hardware register and do a comparison operation between that target register and the counter register. And when there's a match, we can fire off a signal. And so generically, this is referred to as a timer circuit. But there are a bunch of different conditions that you could be matching against here. So, when the counter register reaches all 0 or all 1, that could represent something special. Generally, that's called either the underflow or overflow condition for a counter. And then, as I mentioned before, we could also have a secondary register that we're comparing against. That's like a target register that could either send a signal high or low, depending on what you actually want to do. So I implemented this using that circuit verse simulator that we had initially checked out up in the digital logic section. But I guess I'm trying to convince you guys that it is possible to build these circuits basically from scratch to start building elements that are very relevant to computers. I'm definitely not going to be able to cover computer architecture in 10 minutes. So I think we're going to cut it off here. But I hope you guys are starting to see that all of the elements are coming together. All of the bits of theory that we talked about, however diverse, all feed into this concept that we're slowly working towards. If you guys want to unmute, if you have any questions, anything else to ask, or like observations, I'd love to hear it. But next time, we should definitely be getting into computer architecture. So I know I skimmed over a lot of this pretty quickly. So if there was any section that either didn't make sense or you want to go into in a little more detail, I'd also be available to do that.
Wait, you know that standard you talked about, where for floating point numbers, there's like certain rules that you're following?
Mm-hmm.
So is that all like part of a circuit? Like those rules are defined in a logic gate sort of way?
Yeah, I'll get to this as soon as we get to computer architecture, but usually there's dedicated hardware that does like just the addition and the representation of each of the number types. The computer is generally capable of, at least for signed and unsigned integers, the computer is, like if you tell it it's a signed integer, it's capable of doing operations that are dedicated to like sign extension and like the arithmetic shift and addition will both apply to signed integers. You can tell it to use unsigned integers. With floating point numbers, that's a little different. Computers may or may not have dedicated hardware to deal with floating point. And what I'll get to is there are different ways of treating these numbers. So these rules could be represented in software, like using a library that we're working with, or you could have a dedicated floating point unit, is what it's called, that has the combinatorial logic that is encoded with, yeah, these rules. So it's really up to the computer that you're working with. So it's implementation specific, as a lot of things are. Was there anything about the computer elements section that needs more explanation?
Could you go over the bias again? I didn't really get what that was doing.
Yeah, so it's another quirk of IEEE 754. But so if we didn't have this bias here, the exponent value is an unsigned integer. At least it's treated like that. And so if we didn't have the bias, which is being subtracted from that exponent, we wouldn't be able to represent negative exponents. So in that case, so say we remove the bias, the only thing we can do is move the exponent back. So we can extend the significand. Let's say we have like number 12,000, and we have the significand representing the number 12. We can only move the radix backwards. So we can only add those zeros to the decimal value. The reason we have the bias is so that we can move the radix leftward, so that we can represent these floating point, these fractional values. So if we only needed to move the radix rightward, then we could just use an unsigned or signed integer to represent this data. But the fact that we need to move the radix leftward at all, that's the reason why we need a negative exponent. And so if you notice, this exponent is 8 bits. For an unsigned integer, that distributes to values 0 to 255. And if the bias here is 127, then that means we're effectively, we're representing an unsigned integer, but we're doing kind of the same thing that a signed integer would be doing. So we have the 0 at the center of representable values here. And so if the exponent value that's stored is greater than 127, then we start having our positive exponents. Does that make sense?
Yeah, but what is the bias? Like, what is it? Is it like current, or I was confused?
Gotcha. So the bias is just like, it's a value that's built into the standard. So if you have something that's implementing IEEE 754, it's going to do this like exponent minus the bias operation on its own. Like you never have to worry about it. It's not stored in the number anywhere. It's just part of the standard. As if it's just like this one that we're adding to the fractional value. It's built into the standard and therefore the logic that implements the standard, but you don't have to worry about it.
Okay, got it.
I was gonna say the bias is kind of like, that's for our interpretation of it, right? But it's not like anywhere in the computer's representation.
It's not in the binary value representation that's stored in the floating point number itself. It is part of the standard, so the computer logic needs to implement it such that we can get to the correct values, sure. And for our edification, yeah, we need to know that it exists so that we can arrive at the correct value just by interpreting these fields as well. But it isn't actually stored in the number anywhere.
Okay.
The only fields that are stored in the IEEE float are sign, exponent, and fraction.
Okay,
So you
so,
have to,
oh, sorry, go ahead.
so do you have to feed it numbers like accounting for that bias, or would you just put in whatever numbers you like binary representations of that?
Yeah, so typically we don't actually construct floats by hand at all. And that's kind of what I was hinting to earlier. Like we don't usually build a floating point number. There is, there's an online calculator that I've used before. I think this is it. Yeah, so you can, in theory, construct them by hand, just by like toggling bits, see what you get. But typically, we only care about the representation, again, when our application sees that there's like a tolerance that's not being hit. So if we wanted to represent 2.5, the faculties that we have for working with these numbers generally will do that conversion for us, and we won't have to worry about it, luckily. In a lot of cases, you're also not constructing unsigned or signed integers by hand, but it's very helpful to know the representation as like a means of doing like bug checking or validation when you're implementing either hardware or software. Also, if you get into like computer networks, bit representations become really important there as well, because they dictate kind of how you can transmit information. And I'll talk about that later as well, because we'll do a little bit of networking for the project. But yeah, generally you don't work with floating point by hand, and I would highly recommend against it if you can avoid it.
Okay, so it's useful to know the unsigned and signed ways to be able to actually interpret those, but it's not as useful to do that for floats. You just kind of let the dedicated.
Yeah, I would definitely recommend knowing unsigned integers like the back of your hand. Signed integers are useful to know as well. Floating point, I wouldn't recommend like keeping up to date with the implementation unless your application really needs you working with floats directly. So like if you're a hardware designer for building computers from scratch, that's when you need to know this stuff. If you're representing floats in a network transmission, it might be helpful to know that as well. But then again, you could just take the binary values, throw them in a calculator, and have it do that for you. Yeah, the reason I showed you guys this one is just so that you can understand that there is a standard and there is a way of representing fractional values.
Michael, on another note, the logic gates, like chaining them together to actually get some sort of meaningful output.
Mm-hmm.
I know in like CPE and some EE courses, like we go into kind of how you get that from the truth table and like turn that into logic gates.
Yeah, I did.
Is that something that you do? Yeah, well, that's why like I figure, I don't know, is that something that you really need to know, or you only really need to know it if you're like, how often do you actually go into that level of detail with like?
So that kind of depends on what job function you have. If I'm talking about doing just microcontroller development, I never touch this, ever. If as an engineer you have a need to include an FPGA in your system for some reason, then you're likely going to be working with this, maybe indirectly. So if you like, if you're doing FPGA work and you're compiling from C and you're using some kind of translator, then you don't really have to do this unless you're validating your design. But if you're building it from the ground up, like if you're designing a new kind of computer or designing an integrated circuit, that's when you absolutely need to know this. Really, for the microcontroller's sake, the reason I'm showing you is for your edification of like, there is a path to get from basic electronics all the way to microcontrollers, where some cases it's helpful to know, like knowing what memory is and the fact that it's individual cells of bit storage is really useful in some cases. Knowing that one of your signals in your computer may be selecting a state is also helpful. But generally, the computer architecture itself, as a microcontroller developer, you can be agnostic to. There are some cases where it matters, but I don't usually find myself in these weeds in particular.
Gotcha. Sweet. Well, so we're just at 12 right now, so I think we're going to cut it there. Thanks, Michael.
Absolutely.
And thanks everyone for coming.